Okay. Good morning, everyone. This is this will be the third lecture of the semester. I'm giving it another try here. I think I have all the technical stuff worked out, and we should be in good shape. So we're going to finish chapter 1 today, and there is not a lot of mileage to cover, but the miles that we will cover are very important. And so we're essentially going to introduce this idea of a bonding diagram and sort of graphical representation of molecular orbitals. And this is how we'll talk about bonding for the rest of the semester. So, everything that we discuss is grounded in mathematics and quantum mechanics, but in a practical sense, that's not very useful for thinking about structure, bonding, reactivity, inorganic chemistry. And part of that is we don't need as much detail as quantum can provide. And then the second thing is the systems that we look at are often just too complex to be tractable on any to analyze by quantum in sort of real time. So we use these models. So we use these graphical depictions, and their simplification. And part of the consequence of that is we're going to essentially use different rules when we assemble. When we decide where to put electrons, when we assemble molecular orbitals from atomic orbitals. And we're going to take these rules at face value. And I'd like you to trust me when I say that they're founded, they're sound mathematical bases for what we're doing. But as organic chemists, we're more interested in just the qualitative application of these theories, and so we're not going to get into the underlying math. And so, in avoiding that, you have to take what I'm saying at face value and sort of accept it as fact. And for those of you that go on to quantum, you will get the mathematical basis for everything that I'm saying, which when I was a student, I just found that to be incredibly exciting, because everything kind of like goes from being pictures and very qualitative to equations and very quantitative. So, all right, so let me just give a brief summary of where we left off in the last class. So we said that electrons are defined by a wave function, and the wave function has 4 terms. We introduced 3 in the last class. So there is n, which is the principal quantum number, and this is n equals 1 to non-zero integer values. There's L, and this one goes from 0 to to n minus 1. And then there's m sub L, which goes from minus L to 0 to plus L, okay? Those are 3 terms that appear in the wave function to describe an electron, okay? There is a 4th term which we need to introduce, and fortunately, it's relatively straightforward. It's m sub s, or the spin, and for an electron, m sub s can take 2 values. Okay, plus 1/2 or minus 1/2. Okay, and so the first 3 terms define the orbital. So where we get the shape and the directionality of the orbital are from those terms, okay? The fourth term defines the spin. Okay, and we typically represent the spin with a little half up or down arrow. So, and it doesn't matter how you assign plus or minus 1/2 there. It's just, the point is that, you know, this is showing us the two options in terms of M sub S. And so using these four terms describe an electron in either an atom or a molecule, okay? And there's an important principle known as the Pauli exclusion principle. And this states that no two electrons can have four identical quantum numbers in the same molecule or atom. Okay, and so what I can do is, so what this means practically is that you end up with two electrons in a maximum of two electrons in any orbital. So you can have n L, m sub L identical, okay, but then you have to have some difference between any two electrons. And so if they share an NL and m sub L, m sub S has to be different. I only have two options for m sub S, and so what I'm stuck with is two electrons in any orbital. So okay. And when we left off on our last class, we said that we had looked at three different types of orbitals. So the first was the 1s orbital. Okay. The second was the 2s orbital. Okay. And then the third types of orbitals, of which there were three, were those 2p orbitals that we looked at. So let's see if I can erase that. Okay, so draw. So okay, so this is 2s, and then x, y, z. Okay, 2px, 2py, and 2pz. Okay, I can define, or I can list the quantum numbers under each of these. So if we could make a little chart here, so n, L, m sub L. So here n equals 1, and L is going to be 0, m sub L equals 0. Okay. In the 2s orbital, n equals 2. and L is now going to be equal to 1, and M sub L is going to be equal to 0. I'm sorry, I misspoke. L for the 2s orbital is 0. It's going to be 1 for the 2p. So L is 0, and that forces M sub L to be 0. Okay. But then looking up here, we know that L can go from 0 to n minus 1, and that's where the 2p orbital is derived from. So keeping n the same, but then now letting it be n minus 1. I can then get 3 values for M sub L, right? And so this can be -1, 0, and then +1. And these are the same. Okay, so these are the terms that correspond to each orbital. Okay, and we can then, with M sub s, introduce up to 2 electrons into any single orbital. Okay, so I'd like to talk a little bit about the relative energies of these orbitals, because this is important. And the answer is that the energy increases as you go away, Doc. As you go from left to right as I've drawn them. So okay. And what do I mean by the energy increases? So remember, the orbitals are a state that is available to an electron. It's a place it can go. It's an empty seat in an auditorium. You know, you can conceptualize it however you like. Those states have defined energies. So it's as if, you know, maybe think about it in terms of, you know, riding an elevator, right? The higher you go, the more energy you have, the more energy it takes, right? And you know, you can get off at the first floor, the second floor, the third floor. You can get off at the 1s orbital, the 2s orbital, the 2p orbital. You can't get off in between floors, right? So it's very discrete. And so it's a similar situation here. If I'm an electron, I can go into a 1s orbital if it's available, and that'll be the lowest energy state. I could maybe go to a 2s orbital, okay? That's slightly higher in energy. But if I have my preference, I'm going to go to the lowest energy orbital. And what I mean by preference, if the option is available, if that orbital is empty. And that brings us to what we call the Offball principle, which is just codifying what I just said. So make sure I don't misspell this. Okay, so it's an intuitive principle. It says that electrons are going to populate the lowest energy orbitals first. And we only start working up to higher energy orbitals once we fill what is the lower energy ones. So for hydrogen, there's 1 electron, and so it's going to sit in the 1s orbital. it is not going to be in the 2s orbital. When we start to populate bigger atoms, you'll see, hopefully, maybe perhaps it'll be a little more apparent. So if you consider carbon has 6 electrons, okay? And so if I just go through the orbitals, 1s, and I'm not going to specify their populations. We know that the 1s is lowest in energy, so the first 2 electrons are going to go there. The 2s is the next lowest in energy, so we put 2 electrons there. And then, and only then, do we start populating the 2p orbitals. Okay, so fill those low energy orbitals first. There's a question as to how we distribute the electrons in the p orbitals, and there's another sort of rule that we can follow, and that's Hund's rule. And Hund's rule says that you fill degenerate orbitals before doubling them up. And by degenerate in this context, we mean orbitals of equal energy. And so the 3p orbitals, they differ in directionality, but they are otherwise the same. Okay, same shape, same distribution, same nodes, same energy. And so I'm going to put 1 in the px, 1 in the py, and that is the ground state configuration of carbon. So let me just write down Hund's rule. Okay, before doubling up. Before doubling up. And so why do we do this? Why do we fill the degenerate orbitals first? If you consider, if we just draw, for example, the 2px and the 2py orbitals, okay? Suppose that I populate each one of these orbitals like that, okay? According to Hund's rule. The other option would be to of course, double them up, okay? And the advantage of populating the degenerate orbitals is that you're spreading out like charges. If I were to double them up, you end up with a bit of electron-electron repulsion. And so that tends to be a higher energy configuration. And so the electrons occupy the orbitals in a singular fashion before you start pairing them together, okay? And so we've defined sort of the quantum mechanical terms N, L, M sub L, N sub S that describe an electron. We said that no electron in any atom or molecule can have 4 identical quantum, or no 2 electrons can have 4 identical quantum numbers. And we said that there's a few rules that we need to learn when we're filling atomic orbitals. So there's the Offball principle, fill the lowest energy orbitals first. Hund's rule, populate degenerate orbitals first, okay, before doubling up. And so we've applied those to atomic orbitals, and they translate faithfully, or they apply equally to molecular orbitals, okay? And so I'd like to discuss how we build up molecular orbitals and how we like to talk about them in the next bit of the lecture here. So right, and in order to understand what we're doing, I just need to mention the wave function, and this is be one of the the last times that we're going to really talk about this. Wave functions, like any function in math, can be combined in any which way that you want, right? And so if you add both sides of an equation, that's completely legitimate. And so what we're doing mathematically when we generate these MOs is combining these atomic wave functions. And again, we're going to not do it using equations, but instead doing it graphically. So okay, so I can say, all right, I want to make a new molecular orbital. I can take all of these atomic orbitals, start adding and subtracting them. We're going to really limit most of our discussion in the class to instances where you combine 2 atomic orbitals, but there's no reason that you can't combine 20. And it's very common to see 3, 4, sometimes even 5 put together in organic chemistry. But fortunately, we don't have to go there, at least not right now. All right, so mathematically, we can form these more complex equations. Graphically, the graphical equivalent of this is going to be to take 2 of our orbitals of interest, 2 shapes, and add or subtract them. So, for H1s, for the H1s orbital, I can combine them in 2 ways. I can add them, and I get the orbital in the center here, and we refer to this as a bonding orbital, bonding molecular orbital, or I can subtract them. And the key point is that if I subtract them, the sign of the second orbital changes, and so you wind up with a node. And we call this an antibonding orbital. And strictly speaking, again, this won't really come into play too often, but we may occasionally need to remember this. A bonding orbital is defined as an orbital, a molecular orbital that has more bonding interactions between nuclei than anti-bonding interactions. Okay, and the corollary is true for an anti-bonding orbital. So if I look at the H2 bonding orbital that I just drew, we can say, okay, how many bonding interactions? Well, there's one between two nuclei. How many antibonding orbitals or antibonding interactions? 0. So that's a bonding orbital. You go to the other combination, how many bonding interactions? None. And then how many antibonding interactions? 1. So it's an antibonding. And obviously, this is like a self-evident example, but you'll see you can generate MOs where you have, an antibonding and a bonding interaction, and you sort of need to figure out how that, what the net sort of the sum of those are. All right, so I'm going to record this lecture as 2 clips, and so I'm going to stop right now, and then we're going to just pick it up, and so this will make it easier for you to download and things like that. So